Alright, so today I'm gonna be explaining another important article on graph representation learning with the title Measuring and Relieving the Oversmoothing Problem for Graph Neural Networks from the Topological View. So this important paper in 2019. So graph neural networks have achieved promising performance on a wide range of graph-based tasks. Despite their success, one severe limitation of GNNs is the oversmoothing issue, indistinguishable representations of nodes in different classes. In this work, we present a systematic and quantitative study on the oversmoothing issue of GNNs. First, we introduce two quantitative metrics, MAD and MAD gap, to measure the smoothness and oversmoothness of the graph nodes representations respectively. Then we verified that smoothing is the nature of GNNs, and the critical factor leading to oversmoothness is the low information to noise ratio of the message received by the nodes, which is partially determined by the graph topology. Finally, we propose two methods to alleviate the oversmoothing issue from the topological view. MAD-REG, which adds a MAD gap-based regularizer to the training objective. ADA-EDGE, which optimizes the graph topology based on the model predictions. Extensive experiments on 7 widely used graph datasets with 10 typical GNN models show that the two proposed methods are effective for relieving the oversmoothing issue, thus improving the performance of various GNN models. I've talked about this MAD performance in a different video, so I don't repeat it. MAD and MAD gap are very important measures for oversmoothness. So these are the data sets and models that we use. For example, we use GCN, we use GraphSage, higher order, and the metric, as I said, is MAD. MAD is very popular metric for smoothness. And here, so given a graph representation edge, we use hidden representation of the final layer of GNN, of course. And the term edge is the hidden size. We first obtain the distance matrix by computing the cosine, but do you think this has been implemented in our brain? So you see, our biological neural network is far more advanced than these things. So d sub I j is the distance between I and j, cosine distance between each node pair. So hk is the case. This is the case row of h, and the reason to use cosine distance is that cosine distance is not affected by the absolute value of the node vector, thus better reflecting the smoothness of graph representation. Then we filter the target node pairs by element-wise multiplication with a mask matrix. So now we access the average distance for non-zero values along each row. Finally, the MAD value given the target node is calculating by averaging the non-zero values in D bar. So you see, for different models, for example, GraphSage, let's say, for GraphSage as at different number of model layers, you will see that the MAD values of GraphSage. So information to noise largely affects oversmoothness. So we propose to use the graph topology that approximate node category and calculate the gap of MAD values, differentiating remote and neighboring nodes to estimate the oversmoothness. So MAD gap is just MAD RMT minus MAD neighbors. And MAD RMT is the MAD value of remote nodes in the graph topology, and MAD neb is the MAD value of the neighboring nodes. So remote nodes, neighboring nodes. So large MAD gap value indicates that the useful information received by the node is more than noise. The graph topology is constructed based on natural links. For example, the edges in the citation network represent the citing behavior between papers, and edges in the product network represent the product's co-purchasing relations. In summary, we find that the graph topology has a great influence on the smoothness of graph representation and model performance. So we see MAD gap as a regularizer, and this lambda is just a hyperparameter to control the influence of this MAD regularizer. So after optimizing topology based on gold label, the oversmoothing issue is notably alleviated and the model performance is greatly improved. And then they do relieving on higher order layers